server. So the agenda today, I want to cover like three main topics. So firstly, I'm going to talk about something called the actor model, which is a reactor-based way of programming systems. Then the next section I'm going to cover is transactions and also something called software transactional memory. And the main gist of the talk is to combine those two concepts together and create something, something hopefully a little bit better than either in isolation. And then I want to reserve about 20 minutes of the talk to a live coding demonstration. Well, a coding demonstration, parts of it will be live and parts of it will be pre-canned. So first to give some, tell you what it's not going to be about, because I'm going to be covering quite a few topics, and each topic can be like quite in-depth. So this earlier talking about actors is quite an in-depth area. Simply transactions is a huge area. So I'm not going to give you an understanding in depth of these topics, but what I will do is I'll have at least a slide on each of them, a slide or two, to give you an overview of the ideas, just so you can understand what it is that we're combining and understand what the demonstration is going to be about. As well as the concepts, the talk will introduce some technology that embody those concepts. So there's Vertx, which is like really the representation of actors, the Narayana representation of transactions, and then we'll be running it, some of the parts of the demo will be running on a container application container platform. So first area I want to cover is what's called the actor-based program model. So the actor-based program model is a way of like modelling concurrency in distributed systems. So it's a topic that was been around since the 80s, maybe even earlier than that, 70s, 80s. So it came from from academia and research, and people researching, looking at the problems of distributed systems and how to make sure you get some safe programming in a distributed system. So another related concept is CSP, which is communicating sequential processes. So that's the way the two models differ is that one does synchronous communication, CSP, the other one, the actor model, does asynchronous communications. So in its essence, it's a very simple model. So the diagram I've got at the top right there shows what's there, embodies some processing. So that's the actor. That's the actor itself. It's got needs processing resources, and it's also needs to embody storage. So the storage is modelled as a queue or a mailbox in the terminology, and the core idea of the model is message passing. So everything really is about the messages, and the other parts of the system is really behind the messages. To give that such a simple diagram a little bit more context, concrete context, as you might use it in like a real system. So there's an example, a contrived example, but perhaps not. So you can the idea of a trip. There's a trip actor, and a trip actor, when it receives a request to do a trip, then it needs the services of other kinds of actors in the system. So typically, it might be a taxi and theatre bookings, airplane bookings, etc. So what it would then go in and do is create some new actors, because actors can do a number of things. So they can create other actors. They can when they're doing message passing, they receive a message, and in response to receiving a message, it can go and create new actors. It can send messages to other actors, or it can update its internal state. So in the model, that's called designating the change of behaviour to do on receipt of the next message, but basically it's just how it modifies its internal state. So if you see the messages there, there's no direct communication between the actors, it's all done through a mailbox. So what that means is that the process entity, the actor, can run, it encapsulates its state. So its state is private, so you can't directly manipulate the state of another actor. And as you see on the next slide, that brings some interesting benefits. So yeah, so some of the features you get is the actors respond to messages. So normally what you do in an actor-based system is you have fixed message sets. So an example is in REST HTTP communications, where you have you have different verbs, and different RESTful services will respond to certain types of messages. Also, as I said, the data management is simplified, so you can reason about the state more easily, because you know that the state is not being modified by other actors in the system. And because like actors only know about other actors in terms of the addresses, the address is a little bit like an endpoint, and because it's just an address, it's an arbitrary address, that gives you location transparency. And it also gives you the loose coupling if you're not looking at other tracks of states. So yeah, there's a lot of things in common with this, with the traditional object-oriented model. So you might be wondering why they're different. But the object-oriented model is also about passing messages around, but those messages go to interface and they're synchronous. So because like the effectively with an object, because it's a synchronous call, it's like the context being propagated around the system. So that context is the thread. So the thread is really part of the object-oriented model of computing, whereas the actor, there's no concept of thread explicitly in the model. It's like I said, it's just messages being passed around the system. So with the way that object-oriented program was designed, because of this synchronous aspect, so when you make another call to another object, you've got to wait. So effectively it's a blocking call. Generally it's a blocking call. You've got to wait for the response, and then you've also got problems if there's other objects in the system sending messages to another object. You've got issues of re-entrancy going on, and now you've got two threads entering an object and they're both modifying the state. So all of a sudden you've got this encapsulated state which you're supposed to get from orientation, and then you've got two different entities mutating states simultaneously, which ought to be encapsulated. So it kind of breaks some of the ideas of why OO was first invented. So it kind of like gives you a little bit more than the object orientation by pulling out that concept. And then at the bottom there, so modern systems, it's all about getting throughput in the system and like making sure that you're getting like full utilization of resources, because obviously we've hit the limits of things like Moore's law, etc. So you need to take advantage of all the cores. So we tend to be like build more cores rather than more computers. And then the reactive way of programming enables you to like maximize the utilization of your resources on your computer. And the actor model gives you a nice, easy way of making sure that you fully utilize the resources. So related to this topic that I want to discuss today is the transactional aspect. So I'm going to give you just a quick brief overview of transactions, so particularly distributed transactions. So a transaction gives you like some kind of consistency properties when you're like communicating between entities in a distributed system. So two entities talk to each other, and it gives you a way to guarantee that that you've got some kind of consensus in there. So a transaction. Normally, when you talk about transactions, you talk about these particular characteristics, properties called acid properties. So the atomicity aspect is really saying that at the end of the transaction, that's when things happen. So, and at the end of the transaction, that's when everything gets committed and becomes exposed to the rest of the environment. That's the isolation aspect. And also, in between these brackets where you start and stop the transaction, that's where you've got the consistency. So once you complete the transaction, the programmer has done his changes inside the transaction, and he knows that when he's going to commit the transaction, things are going to go back into a consistent state again. And that's how you maintain program correctness with transactions. And then there's the fourth item there, is normally with ACID transactions, the durability aspects, and that's to support like failure scenarios. So if you're in the transaction, you've maintained a record of everything that's been running in the transaction, all different participants, and those are made durable at some point, so that if you do fail, if you get disasters, because you will get disasters in large-scale distributed systems, then you know that you're not going to be compromised, and the state that you had there is going to be brought back again, and you better complete the transaction. So those are the properties you get of a transaction. So how does a transaction manager make sure that those properties become manifest? And it does it through a two-phase commit protocol. So basically, you've got different parties involved in the transaction. So as the transaction runs through, and the different parties are doing their various pieces of work, and when time comes for you to terminate the contract, the transaction manager will run through all the participants that have taken part in that transaction and say, are you prepared to make the changes that you've done in the transaction? You try to make them permanent? And then those participants will respond yay or nay. If they respond yes, then you know it's going to be okay to go ahead and try and commit the transaction. So that's a requirement on the participant. If he says yes, he can commit the term, that he's prepared to commit the changes, then he has a responsibility. He has to make sure that that he knows he's done that. So if you get failures, it knows that it can go and and complete its work. So in the jargon, those would be like XA resources. So the thing that coordinates all these different participants and coordinates the beginning and the termination of the transaction, that's called a transaction coordinator. And like I said, there's requirements to have durability of a transaction, and to do that, the transaction manager will have what's called a transaction log. So when it's done the prepare phase and knows what all the decisions are going to be, it's going to write a log, and that log will survive crashes and disaster, so that a recovery part of the system can then pick it up after problems. And the general terminology for that protocol I've just described is 2PC or two-phase commit. And the picture on the right there has analogies with the managed ceremony. So I won't say the analogy, but I'll leave that as an exercise for you to work out where the similarities lie. So there's a kind of model of how to do transactions called software transactional memory. So that has many of the aspects I've just talked about there with ACID transactions. It's not a full ACID transaction, but it has many of the properties. So this software transactional memory, it's still an active area of research. It was popularised in the 90s, but prior to that there was hardware transactional memory. But in this talk it's all about doing it in software. And it's really designed for when you're running in a system, a highly concurrent system where you've got lots of threads all trying to modify state simultaneously, and it gives you protection in those kind of systems. And it's really I know that there are transactions available already, but it's about ease of use. So it's simplifying the way that you can get transactional guarantees in your programs. And like I said, the whole idea is to really make it very, very simple to get these transactional guarantees. So the idea is that when you're going to, when the parties involved have identified some state that they want to be able to share and that they want to protect, then any changes to that state has to be done inside a transactional block. The transactional block, so you've got in various implementations of STM languages, you have a primitive or a library call just to demarcate your set of instructions that you want to protect with this software transactional memory technique. So so there's various flavours about how you do this, how you do your locking, or how you maintain the guarantees that this system gives you. And it's optimistic and pessimistic are the most the two main different ones. So with the optimistic one, it's similar to JDBC's database systems. So with optimistic approach, you don't lock as you go along. You just record what you've done. And then at the end of each transaction, when you're going to commit, at that point you start taking your locks, or you'd look at your timestamps. And the alternative is your pessimistic approach. So the pessimistic approach, you take your locks as you go along. Obviously, the pessimistic approach it means that you won't be doing computation that might be thrown away, whereas an optimistic approach, everybody does what it needs to do at the end of the transaction. That's when you start looking at locks. But it means that if you've got high contention, you've got a lot of potential work that different threads have done that needs to be thrown away, and that might be expensive work. So you have to think about, what problem you're solving in your code, whether you want to use optimistic or pessimistic. So the way to break out, for example, a pessimistic approach based system. I know that traditional systems have lock-based approaches to concurrency control. So you could get deadlock, but this STM approach gives you things like timeouts, or it gives you retry options if you find a lock's already been taken. Or a very good solution is just throw an exception and force the programmer to handle the exception and realise that what he wants to do. You can either go and try an alternative piece of work, or you can just rerun the transaction, for example. And it gives the programmer a lot more control if you just throw an exception. But like I say, there's these other techniques like timeouts, I said, or retries. And like I said there, typically the durability properties because this is software transactional memory, typically it's running inside a single JVM where you're protecting against access from different threads that you want to get your concurrency control. And with those ones, you don't necessarily need the changes to be durable over if the JVM crashes. But you know, some systems do have durability, other systems don't implement it. So some of the characteristics you get from it is like you get isolation. That's slightly different from the ACID isolation. So the isolation is that if you're running a transaction, it may be that, you know, non-transactional threads that are running, you know, do they see the change that other transaction threads are making, or are they hidden? So, and again, like typically they're isolated for each other. So, for example, if you've got a transaction already operating on some state, and then another piece of code actually wants to make changes to the state as well, then the STM implementation will upgrade that call to a transactional call automatically. The granularity of your the memory that's being managed by the transactions. So the typical one these days is object-based. So the unit of your transaction memory that you're being protected by the transaction is your object. But you know, in hardware implementations, you're talking about blocks, or you talk about actual words. So you can get fine-grained. But that has problems because every time if you're like touching bit of memory, then the system has to like track all the changes that are being made to it, so that it knows what to do at the end of the transaction. So if you're doing it at the object level, then you know object's already has already got lots of metadata associated with it. So it's a small step to add extra metadata to say who's been touching these objects. Whereas if you're working on a word or a cell boundary, you can imagine it's going to be very complicated to do in an STM-based approach, and it's going to be very resource hungry on memory that you're going to be using. Another aspect, characteristic of different implementations is like the support for nested transactions. So if you've already started a block of code, you've got your atomic block, you're running through your code, and then you go and call another bit of code, which is also bracketed as an atomic block. Then you know you've got choices about, do you start a new transaction in there, or do you nest it under the existing one? And then that has like the nesting properties that you might want. So I know there's an earlier talk today where you talked about nested transactions. So it's in STM, there's different flavors of nested transactions, but it's the most typical one is if the, I won't go into too much, if the nested one like both, then the top level continues, the nested one commits, then those commits are not exposed to the environment until the top level one commits, etc. There's also the question about what happens if you get exceptions while you're running the transaction. What do you do with those? And does your STM implementation, does it retry the block of code, or does it run some handlers, or does it just let the programmer handle it? I briefly mentioned that earlier. Personally, I think the best approach is just let the programmer handle it, and it gives him the maximum flexibility, and it means he doesn't have to go and catch specific exception types, so he doesn't pollute his code with the STM library's implementation of its exception types. Because the whole idea of what I want to get across in this talk is how simple it can be to write an STM system. So, yeah, the main bit that I want to bring out in this talk is combining the two approaches. So, okay, those two approaches I've talked about, I've already said they've been around for like decades even. But it's when you combine them that I think you can get some very nice benefits for when you're building like these reactive, scalable, elastic systems that we need to program to these days. So you know, in the days of microservices, it's no longer like the monolith approach is no longer the only approach. So a stateful actor, so an actor like maintains its own private state, but as he goes through its system, he's changing things. Also, an actor can present a facade, if you like, with its mailbox, and it implements its behaviour through like running other actors. You might get failures while the actor is doing this state. So it can be some systems might find the benefit to have some form of way of like guaranteeing consistency amongst these different situations. Yeah. So I'll give you some examples later on when I come to the code demonstration. So yeah, so the combination of two is fairly natural, and I think you can get a very persuasive benefits from combining the two. And as it turns out, many actor-based systems already provide STM solutions. You know, things like Akka used to have transactors. Scala's got a Scala STM library. And if you pick out the most popular actor-based languages, they do have some kind of support for STM. There's also Vertx, which uses Narayana STM solution, which is what I'll be using in the demo later on. So in the demo, these are the technologies that I'm using. So the Vertx is to correspond to the actor-based approach. So Narayana has its own implementation of a software transactional memory. And then when I want to scale that out, so I'll be running it on a cloud, on an application container platform called OpenShift. So Eclipse Vertx. So Eclipse Vertx is a reactive-based system. It's non-blocking. It works on the level of an event bus. So events come into the system, and Vertx manages the event bus, and you register handlers against different events that are put onto the event bus. And then Vertx calls those handlers. It can do load balancing across different handlers because it knows that it can assign it to different Vertx verticals, as what they're called. It's got support for doing more than just that. It's got things like failover, circuit breaker. So all the things you want to make your system resilient. It's also got clustering support. It's polyglot, so it's only rough for languages running on the JVM, but you can write your system and then you can compile it, you can generate other language bindings. And the language bindings you get are conform to the idioms of the different languages, so it's not like you're programming against it's not contrived interfaces, it uses the same idioms. And then it supports different kind of transports and different kind of event bus technologies, so InfiniSpan, Spring Boot, etc., so AMQ, different various underlying transports, as Google RPC is supported. There's also transactional support using this STM solution that's provided by the Narayana project. And it's got a very large user base of contributors, so it is a very popular language, popular library. So then there's Narayana STM. So Narayana provides its own STM solution, and it defines the STM at the level of objects. So your transactional memory is in the object. You have two kinds. You have volatile. So a volatile one doesn't have the durability aspect, so if you crash then you lose your changes, but you've still got your transactional guarantees where you've still got your atomicity, etc. Or you've got your persistent one, so if you do crash and the system comes back up again, then the object that you've been changing is still there available, and if it was in the mid-transaction, it'll continue that. It supports both pessimistic and optimistic models. You've got different variants of nested transactions. You've also got modularity, so it supports the context of the transaction block that you're running and propagates them as you call other threads. And it's annotation based, so that's for, again, as I said before, it's about simplicity of programming approach. So to get the benefits of the STM solution, you just annotate your code, and these are some examples. So I'll maybe talk about these ones when I come onto the code demonstration. And at the end of I've also got a demonstration showing all this stuff running on OpenShift. So OpenShift is a layered architecture, it's a container-based application platform, and it builds upon Kubernetes, and it makes it nice and easy to use and build some extra things such as build and deploy like pipelines on top of like Kubernetes lifecycle approach. So now I'm going to do the coding demo. So if I move over to an IDE. So what I've got here, so because it's for demonstration purposes, it's a very simple example. It's not very complicated, but it's mainly designed to bring out and make it clear and evident how you get these transactional memory guarantees. So it's just a basic Vertx event-driven application. The Vertx event application, the main application extends a vertical, and then the Vertx runtime has an event bus, and it knows that this particular vertical is listening on the event bus. If you go and look down, so there's that's where in the main you actually deploy your vertical, and then the start method. So when this vertical's runtime starts up, it goes and introspects all your classes you've got, and it figures out that okay, these are all the verticals you've got, and it calls the start method of all the verticals that it finds on the class path. So this is like a web application. So it creates an HTTP server down here. It's async, so you've got a request handler, and then you say the handler, what I'm going to do is I'm going to call the accept method on a router object. And that router object is what the application developer defines to be for the behavior of his service. So, so there's the router, so he's going to accept post call. So when a post call comes into this application server, the Vertx runtime is going to invoke this lambda. And there you got the lambda as the request comes in. And all that lambda is doing is effectively is making a booking. And the booking is really just incrementing an integer. And then it's printing out the thread. So if you go and quickly have a look at the make booking. So the interface is get how many bookings are being made and then create an increment the counter for the number of bookings. And then the implementation is, there's the implementation, just a very simple thing. It implements the flight service interface and all it does is return this counter. So if we go and run that, so I've got to start Vertx running. So that's Vertx running. This is a Fabricate plugin. So what it does is it starts it running and that looks for all the different verticals you've put on your class path. And then if you have a look, and then you can issue some requests on it. So if we look at so the RESTful API endpoint is on this URL I've put here. So if you do that, you issue requests on it. You can see it's a single thread handling each one. But because Vertx is an event loop based application, there's only for each vertical it runs a single thread. So if you've got it does it on a per core basis, but it makes sure that that thread running on the core is fully utilised. So it's not only necessarily this particular vertical I've done. There might be other verticals in the system, and if there's one that doesn't need running, it just keeps running them. It keeps invoking those ones and maximises the utilisation of that particular thread. So you don't get thread context switches in Vertx. You can also, I can show here, throw lots of concurrent, so this stress test is throwing lots of concurrent requests, HTTP requests at it, and it's going to do, it's on a parallelism 50, so it's going to run from 50 different threads are going to fire requests at it. And it should come back with 5,001 requests, so if you look at there, so it did 5,000 requests, none of them failed, and if you go and have another look at what the current value of the counter is, you see it's 5,003, so 5,000 plus the other ones that I did. So what it's showing that there was, even though I did 100 concurrent requests at it, there's no been interleaving, no problems. But you might get a situation where you would like to really increase the throughput of this Vertx application. So currently it's designed to run on just a single core. So you might have a multi-core machine. So this particular one's got 8 cores on it, and 7 of them are sitting there idle. So it'd be nice to be able to utilise all those cores. So the way you'd do that is you would deploy 8 instances of this vertical. So if we go back to the main vertical, there was a deployment method there, set instance, and only got one in there. So if we make it 8 the number of cores I've got. Oops. So now what the system is going to do, So now what first it's going to do, it's going to go and deploy that vertical 8 times. Did it actually do that? So now if we have another look, the booking count there is 1, do another one, booking count is 2, but if you look there, the thread, so I've got thread 3 handle the first request, thread 7 handle the second request, so that demonstrates that the different verticals running on different threads are handling these requests. And then you can stress test it as well, and you can run your 5,000 requests at it again. So, not sure what's going on there. So I did have this problem early on where if I was connected to the wireless, it caused a problem. So let me turn the wireless off. So Wi-Fi. Let's turn that off. Start that again. Yeah, okay, so it's still running. So if we stress test it again. So that worked. So if now we have another look. So we did another 5,000 requests, and if you look at the booking count now, you see that it hasn't got the 5,000 requests, it's got something quite a lot less than 5,000. That's because there's been interleaving, because this code that I've written isn't thread safe. So we go and look at the problem where it is. So if we go back and have a look at the implementation. So you've got many threads doing this make booking requests, and they're all doing it at the same time. There's no concurrency protection for that. And it's not going to protect, because like the variable that's being updated is local to the core and it's not being shared with the other cores. The other cores are not seeing the updates, so you're getting random changes in that variable because you've got no memory barrier in there between the different cores, so you are going to see some interleaving going on. So how to fix that? The way to fix that is you can either go with the traditional concurrency support mechanisms, or you can use the purpose of this talk, which is the using software transactional memory. So the way you do that, as I said before, it's annotation based. So if you go look at the interface, so the first thing you've got to do is you've got to mark up the interface with some STM annotations. So the only required annotation is the transactional. So what the transactional does is it marks this particular interface out as being potentially manageable by the STM system. And also, normally what you do is you bracket your code chains inside an atomic block. So you start a transaction, do your code and complete the action. But there's one that will automatically do that for you, and so it's a quicker demo. I'm just going to mark it up as nested. So what a nested one does is if there's no transaction context on the thread when the calls are made, sorry. Yeah, so if there's no transaction present, then it'll create one for you, and that's effectively does its own atomic block for you. Then if you go and look at the implementation, there's some things we have to do with the implementation. There's sensible defaults. So by default, all private state is transactional memory, but it's good practice to explicitly tell the system what's state and what's not state. So you mark that up with that state annotation. You also tell it which read and write blocks, so which one are mutating states and which ones are just reading state. So the get number of bookings is obviously is not mutating, it's just reading. So you take a read lock, and the make booking is incrementing the counter, so that's got to be a write lock. You also need to tell the system, the transactional memory implementation, that it needs to start monitoring and observing this interface that you've just put the annotations on. The way you do that is you've got to create a container. So static oops. Containers are typed, so we're going to type it to the flight service. So that's your container. Then you've got to instantiate your container. So container equals, new container. There are various properties of your transaction. Remember I talked about like volatile, durable, volatile ones or persistent ones, and you can modify the shareability of the transaction memory you're creating, and you can do that by passing parameters to the constructor. So to go for the defaults here, which is like a volatile or what's called a recoverable container. So now you've got your container, you can actually use the container to get a handle on that piece of transactional memory we just marked up. And that one is you say to the container, create me a handle representing a flight service implementation. So that's how you do that one. And then each thread now needs to have its own copy of that state that it's going to be changing as its own copy, and then at the end the system will go and look at the different copies, and then it will be able to look for conflict detection and resolve any conflicts that might occur. So each vertical, so remember we've done 8 instances, so you effectively got 8 threads. So you create in this start method, you create a copy of your flight service. So it's a clone of the original piece of STM memory. And then you ask the container to clone it for you. So you've got your member and your proxy. So new flight service import. And then your proxy, that you're proxying is the container that we created at the top here, which is up here. That's the bit of memory. That represents the state that's going to be managed by the system. So now you've got to turn. Now each thread gets its own handle on the bit of transactional memory, and I'll be monitoring changes to that. So I've cloned that, and you've got to make sure you use the clone one in when you're making the bookings, etc. And then if we go back to, let's try running that one. So this plugin recomp detects changes, and the Maven Vertx run plugin detects the changes. So it's seen I've changed the code, recompiled it. So now if I go and issue another request at it, let's have a look, see what we've got. So we've got booking count is 1, so that looks good. So now remember, if I did the stress test before, because there was no like memory barriers protecting the access to the booking counts, we got interleaving and we got an invalid booking count. So this time, because we've got software transactional memory protecting that bit of memory, we should be able to see that we're no longer getting interleaving. So we do one more post, we've got 5,003, so we've just done 5,000. So it demonstrates that there's been no interleaving by adding those STM annotations and by getting a proxy to the bit of software transactional memory. And I hope you'll agree that we didn't have to do very much. So we just marked up the interface, marked it as transactional. The implementation, like by default, every private member is transactional memory, but marked it up. And also by default, every public method is a mutator. So we're going to hint to the system that some of them like the read lock, that doesn't mutate state, but it doesn't need to take locks. So how are we doing for time? So we've got a bit of time left. So the final part of the demo is going to be running on. It's going to be running on a cloud-based application container platform. So for that one, it's going to be something called Minishift. So Minishift is like it provides an environment for running OpenShift on a laptop. So Minishift it needs a hypervisor. So the hypervisor we're using is VirtualBox, and in that hypervisor it runs the OpenShift environment and starts up a cluster of OpenShift nodes, a cluster of 1. But in that cluster of 1, like with the way Kubernetes works, you can have many pods inside that cluster of one node. So in that cluster, we're going to deploy this application onto a node in that cluster, and then we're going to issue HTTP requests at it once it's deployed. And then, as before, when I put the memory protection using software transactional memory, I protect against different threads running on the same JVM. So that's vertical scaling, but I want horizontal scaling. So with horizontal scaling, we're going to be running this application on multiple nodes, and we're still going to get consistency guarantees. So that's going to be less performant. So for that one, we do need to have persistent containers, which won't be as performant, but for some kind of application, some niche applications, it will be. It's a solution in your toolbox, if you like, where there's some applications that might take benefit in being able to share state across JVMs, across nodes. So that's Minishift running. I'd already deployed this application to Minishift, so I'm not going to go and to deploy you use the source to image build with the Maven source tree, and then the plugin I've got here would automatically build the Docker image and upload the Docker image to the OpenShift Docker registry running inside Minishift. But yeah, that can take some time, so I've already done that. So if we now go, let's start the console. So that's the Minishift console. You also got to create a project. So the project I created is called STM demo. And I've already deployed the application. So this is instance number 2 that I'm going to click on. So that's now the application now deployed there, and it's running on one pod. So we can do that by, let's have a look at it. So So I've only got a few minutes left, but it's, yeah, you can go and look at find out what the endpoints are, but I've got one in here somewhere for what the endpoint is. So yeah, so the endpoint here is STM Vertx demo flight, STM demo, and then the rest of the IP address. So each pod is, when it's deployed, it has its own IP address. So let's have a look at that. So if we OC login.
Especially disable the Wi-Fi, isn't it?
Oh, of course, yeah, disable the Wi-Fi. Good point. Let's put that back on in. Right, yeah. So is it time for questions now, is it? Right, okay, so now it's working there. So that's the instance running on mid OpenShift. It's handling the threads, but to show the persistence, I'm going to increase the number of pods it's running on. So now it's going to deploy that simple application onto both pods, and when I issue requests on it, the OpenShift will round robin the requests to each pod. So each pod will get the different requests that will update the booking counter. And because you've got your software transaction memory, you've got your persistent version of it, your non-volatile version of it. So when you issue requests, you should see it being round robin. So there we got one going to flight 2 JGCWG, do another request, and it's gone to a different host, VGVX. So that's showing the requests are being round robined. And you can also see as it goes to each one, the booking count is going 12, 11, 12, 13, 14, etc. So each node that the application deployed on is seeing the same value that the other one's been updating, so you've got your consistency there. It'll also show persistence. So if you go back, and you drop down to 0, so you're scaling down. So now the application is no longer deployed in any pods. So if you run the application, then you should get an error when you go to it. So you get an error, and then if you scale back up again, because it's persistent, then the old value of booking count, I think it was about 12, should still be available. So if we go back here and then rerun it, so it sometimes takes time for them to come up. Let's try that again. Right, yeah, so the booking count is 15. So even though I scale down to 0, that piece of transactional memory is actually still persistent and survives like failures in the system, such as like no pods running the application. Okay, so that's a good point to finish, and I will take some questions now. Sorry? 5 minutes more presentation or for questions?
Yeah, after questions.
Yeah. Well, I've sped up at the end of the presentation there, so I've run out of slides. So I did have some earlier slides where I showed composition of software transactional memory. So the idea there is you've got one object has got some code which is transactional, and then you might want to call other objects, other services in the same VM, and then the transaction gets propagated down to it. You get nested transactions. So you might do that similar to the demo you saw earlier on, where a trip you're doing an order booking and you're booking a flight and various other things. You book your flight and then you book your taxi. You might not be able to book your taxi, it fails, and then you try an alternative. So that's where you would use nested transaction support from software transactional memory. So with the same way with expect transaction, with nested transaction to work, if a nested transaction fails, then it doesn't fail the whole transaction. So you might just fail that part of the change of the system. So you might be able to survive that and try an alternative approach. And then an alternative approach might be to booking a different transport mechanism. So, and that's a nice way to structure applications. So conventionally what you do if you had that kind of system, you'd have to have an API that aggregated all the different changes and made sure the transactions that it was doing was like all the ones it was managing, all the subcores for the services also obeyed the same transaction semantics. So it kind of makes you have to look inside the implementation of these services to make sure that from a concurrency point of view, they're protecting the data. Whereas this compositional aspect of software transactional memory, the system does it for you, and it tracks the different things you've been changing, and make sure it keeps them consistent. And if your top level rolls back, it'll roll back all the services you've touched, even though the top level service might not know the internal implementation of all these other services. And you imagine how difficult it can get if you're having to provide concurrency control amongst all these calls. You might get re-entrancy coming in, and then you pick up another, a lock that's already been taken, depending on how you've programmed your locking mechanisms, like the semaphores, mutexes, etc. And it's very easy to get concurrent software wrong using traditional Java-based concurrency control mechanisms. It's not an easy subject, and the Java memory model is not that easy to understand either, personally. It does make some of these traditionally very complicated problems much easier to program, and you get that concurrency control. And like I said before, you really do need this high level of concurrency in modern systems, because you need to fully utilise your cores that you've got in your system. Because it's all you can't. In the old systems, you used to be able to hang around waiting for stuff if you had big machines. But now, you just got to utilise every single instruction, every single cycle of your CPUs. No, it's not an option anymore if you want to succeed in your modern software. So I will stop there, and I'll take any questions. So if we're done, that's it. Thank you very much. Appreciate you listening. That's great. Thanks very much.